It is 1:30 something, and I have been told it is time to begin. I am now in my box. I'm now in my box. All right, guys, this is the Shepard Test Stand. It's built by a nonprofit called Mach 30, and it is a test stand for ST scale model rocket motors. We developed it in the early 2010s, predominantly actually to demonstrate that you could use open source software practices to develop aerospace hardware, right? We were so successful at this project that we were qualified as open source hardware under the formal definition from the Open Source Hardware Association back in 2016, and we've supported the development of multiple derivative systems. So I'm going to talk today about how we can use Shepard as a case study. So we're going to showcase some of its successes because it's always good to start there. Think about it almost like an agile retrospective for those that are in software development. What worked? What didn't work so well? What are we going to change, right? So successes, our lessons learned, what didn't go so well. And I'm going to discuss our future work, because we are still actively working to support open source hardware development as a methodology, as an approach, as a thing people should be doing, like open source software has done for how many decades now. My name is J Simmons. It is just the letter J. I am an open source hardware advocate and the founder of Mach 30. Like I said, it's a US nonprofit dedicated to developing open source hardware for spaceflight. I was the lead developer for Shepard, which is certified certificate number US 000006, like for real. We are one of the earliest certified pieces of open source hardware in the country or on the planet. We built it for these demonstration purposes as well as education and outreach activities. Like I said, before we got started, used to take it to maker fairs and maker spaces and show it off, right? It is a great way of starting to introduce students to the concepts of data collection, data processing, and you just can't beat watching the motor go. I've also presented at the 2012, 13, and 15 open source hardware summits. I've covered topics ranging from, broadly speaking, open source spaceflight hardware to export controls. You heard that ITAR business in the previous talk. That's an example of export controls. And yes, it's a big deal. Export controls and open source for space is a huge conundrum. We talked about that. And also just open source engineering analysis. How can we do what we are used to doing in the professional field with hundreds of thousands of dollars of software with open source replacements? I was also the chief architect and project manager for Open Design Engine, an all-inclusive web app for hosting open source hardware projects. Especially before GitHub had really taken off, there weren't really obvious places to go put your stuff for open source hardware. And when you did, it wound up in like 7 different places. Here's my WordPress blog, here's my Twitters, here's my BB bulletin forum. Oh, and I put some stuff up in an SVN repo somewhere. And yes, this is all the way back when SVN was still competitive. These days, I tend to focus my effort on collecting the lessons learned on what it takes to effectively develop, collaborate, share, and remix open source hardware projects across the spectrum of settings. Academic, commercial, volunteer. Basically, I want to see hardware developed in the same level of openness and collaborativeness as we develop software in the open source software world. So, we really were focused on this demonstration piece of the techniques, right? We wanted to demonstrate open source software practices on the development of aerospace engineering products. And so from the word go, the development team, which was composed of 9 folks spread across the entire US, all 4 time zones were represented at various points in time. We decided that team of 9 decided to host the project on Open Design Engine, the project I talked about a moment ago, this web application that's a unified platform for this. And that web application has all sorts of stuff that you would want in a project management tool, right? and expands to support hardware beyond just software. So, of course, it had project roadmaps, but it had a non-source code file repository for things like your CAD models, or for distributing PDFs of your assembly instructions or operating instructions, right? That's something that even today is kind of not really a strong suit of products like GitHub or GitLab, right? Because they really assume source code. They want ASCII text that they can diff. You can put PDFs in there, but also, of course, had a wiki. We put a lot of our more frequently updated content, like the evolving assembly instructions, up on the wiki, right? And we had integrated forums. So your user ID that let you edit the wiki or post files to the SVN repo or to the non-SVN repo, let you also discuss the project openly, right? If you were here for the last talk, right, that open project management was a big piece of what we were doing back in the early 2010s. And the tool was built specifically to support that. We thought we had a good tool. We'll come back to that. Now, I mentioned that, that we had derivatives built. So this approach enabled later contributions, that open management style and everything up on Open Design Engine. It enabled later contributors to catch up really fast, right? They could see what we had done before, what we were actively working on, and what we were about to do, just like the previous speaker talked about. But it also enabled staff members of the Coca-Cola Space Science Center over in Columbus, Georgia, where we had no representation of any of our contributors and any of our developers, to build and operate their own copy of Shepard as part of their commitment to hands-on science and technology education. And they got their data too, just like we did. And because this just doesn't get old as far as I'm concerned, here's their version of Shepard testing a motor that they shared with us. Look familiar? They built that simply from the materials available on the project site. What better test of open sourceness is there than someone replicating your work? We were just enthused. I also talked about how we were one of the first to get certified as open source hardware, and that was done under the auspices of the Open Source Hardware Association. But who are they, Jay? What's up with this, right? So OSHW is a US nonprofit organized to host conferences and community events to promote open source hardware as a movement, educate the general public about open source hardware, organize the movement, collect and compile and publish data about the open source hardware movement, and provide a painless way to indicate that your product is open source, really, that it really is legitimately open source. That's where the certification process comes in. So they developed a self-approachable, you go through and fill in a form and go, I did this, I did this, I did this, and someone reviews it real quick, and they go, yep, you're open source. And they actually, because we had been so public in the development of Shepard, OSHW actually approached our team and said, would you be in the first batch on announcement day of folks who have gone through the process and beta tested, and also be in the announcement list of the first dozen teams to have received certifications on their project? And we said, oh yeah, of course we would. And thanks to the diligence of the Shepard Test Stand team, it was very easy to qualify for certification. And like I said earlier, we received US 00006, one of the lowest certification numbers on the planet. And they went back later and listed us as an exemplar project of doing open source hardware. To say I am proud of that team that developed Shepard and put it out there and got that certification is an understatement. Oh, and one more thing that was very cool and totally counts in the success column. The open source nature of the Shepard Test Stand also enabled a father and his two sons that online go by the Jones Boys Rocketry to fork Shepard If you're familiar with open source software, and it was brought up a little bit in the F Prime talk earlier, forking is where you take an existing project and go, I like this, but I wish it did X instead of Y. And so you make your own, and you make your own changes. And so they made a fork to support a science fair project to test their own home-built motors that were far higher thrust level than the motors were that we were testing. So they used our software, our control board, modified the frame, modified the sensors, right? And they found us because the project was open source. They found us on Open Design Engine and reached out on our forums. They signed up for accounts and they went, hi, we want to do a Shepard-like thing. What do we need to do to get started? It's that community building business, right? And they went on to actually win a number of science fair competitions, including one hosted by the American Institute for Aeronautics and Astronautics, the professional association of aerospace engineers. Wow. Did I mention this doesn't get old? Did I mention that this doesn't get old? I have a video of theirs too. This one's a little bigger.
Firing in 5, 3, 2, 1.
Right? And again, it's a real test stand. So they also collected the data, and it was the presentation of the data and the tuning of their motor that got them the science fair wins, all because they had access to an open source hardware project that they could fork. Wow. Okay, so I keep talking about open source hardware, but I don't know that I've quite been clear enough. What do I mean when I say this? Well, this is straight from the definition on the Open Source Hardware Association site. Open source hardware, or OSHW, I'm going to put that on the paper, on the page, the screen, page, this is a screen, Jay, a lot, is a term for tangible artifacts. So not software, things that you can touch, that you build with your hands. Machines, devices, or other physical things whose design has been released to the public in such a way that anyone can make, modify, distribute, and use those things. This should sound familiar to folks that are familiar with open source software. This is a definition that is basically a fork of the open source software definition from OSI, from the Open Source Initiative. And the Shepard Test Stand team really, really honed in on this, especially that business about make, modify, distribute, and use, in case you can't tell from CCSC's own copy and the fork from the Jones boys, right? And we wanted to run this as closely as possible to the not just code drop, but the real openly managed open source projects, okay? And while we did hit a lot of wins, I cannot stress that part enough, we also identified a number of shortcomings in the open source hardware tooling we were using to share and distribute and modify, right? And so we've had a number of retrospectives, and I do mean agile development, big R retrospectives, okay? And the team determined coming out of those retrospectives that what they really needed before people started writing a bunch of tools was a methodology. And what I mean by methodology is it's a fully defined process, right? They needed a methodology that would answer certain questions that tool vendors could then treat as requirements. And specifically, those questions include, what is the source of an open source hardware project? How do you know when you've captured enough material that you can make, use, distribute, modify, That whatever it is you are doing with that source needs to support versioning, branching, forking, merging, and composition. These are the key tenets that get you that use, remix, modify, right? If your tooling, if your methodology doesn't support those 5 behaviors, you're not going to get the definition to happen. Oh, And we really need to enable users to capture all of that in familiar settings and completely, in a way that can be truly shared. So the tooling also has to lean, again, heavily in the direction of open source software tooling. All right? The result of all of that initial retrospective work was to kick off the development of a project, a methodology project, not a tool project, an approach, a process, how do we do these things project, called the Distributed Open Source Hardware Framework, or DOF, because I like engineering puns. And you can go and see the early drafts of content that we created around DOF at this URL. It is all up on GitHub. There's a major rewrite about to begin, so don't take that as the answer. Take that as the first MVP where we went, let's try that again. Now, like I said, there's 3 big questions we have to answer, right? So let's talk about that first one. What is the source of open source hardware, right? I'm going to tell you the first thing is the bill of materials data. And you want to emphasize that word data, the bill of materials data, not the bill of materials itself, right? One of the things that, and that data, right, for those that are not familiar with hardware, right, I'm talking about the list of all components and counts covering all parts and elements which must be procured before you can build the project, right? So, like the stuff that would come in an IKEA box, right? The list of all the things that go in the IKEA box for that dining room table, right? That would be the BOM data, okay? One of the challenges that the Shepard team ran into time and time again is that when you're working with the actual BOM as a document and the assembly instructions as a document and the operating instructions as a document, you make one revision to a part deeply buried in the project, and all of a sudden, you find out that it's mentioned 17, 20 times. No, I meant 21 times in the project. And if you miss one of them, you're providing inaccurate information to the people that want to build, modify, reuse, If you write software, I hope you will recognize that this means that our documents are not dry. They don't conform to don't repeat yourself, right? So what we need is a normalized data structure of the information that can be used to render out the BOM and the assembly. Same thing with the assembly instructions, right? And this way, we can maintain things easier and consistently. You need to update something, you update it in one place, right? It's the same thing about dry source code. Speaking of assembly instruction data, we need that because if you don't distribute the list of parts and the list of instructions, who's ever gotten an IKEA thing without the little white piece of paper that tells you what to do, right? Or had confusion over reading the little white piece of paper, right? You need clear instructions because you are the compiler for hardware. Just ask IKEA, right? So we have to again provide those assembly instruction data, again normalized, and in a way that integrates with the part data, with the BOM data. And then finally, supporting materials, any other required content to build or operate the project. So design files, schematics, the STL files or CAD models, right? Because sometimes the 3D printer is at least one of the compilers involved, right? And I've got to provide the content not only to the human to what they need to do with their 3D printer, but I have to provide the file to feed the 3D printer. Okay? Let's face it, those first 2 items are bare minimum. That last item is partly thrown in there as a catch-all so that we remember to include an extension point in the methodology for when we discover other things that we need to include inside of it. But we had, by God, better get that BOM data and that assembly data into the source, or we're not going to be able to modify, distribute, make, use, Okay. What about this business about branching and forking and merging and all of that, right? Well, let's face it. Software tools in source control and package management and build tools have a decade's head start. So the team decided that what we really need to do is set the methodology up so that you can pick the tool that you think is best suited for your team from the list of package managers, from the list of version control tools. I'm not going to tell you you have to use Git. I'm going to use Git, but I'm not going to tell you. If you want to still use SVN, knock yourself out. I was a latecomer to Git, so I know the you can drag me kicking and screaming to GitHub philosophy. I was there at one point. But we've got to, instead of reinventing a bunch of hardware-specific tools that do these kinds of things, what we need is a methodology that lets you leverage what's already there, or we will be forever decades behind and chasing to catch up to the open source software tools that do the same thing. So it's a fundamental part of the approach to developing this methodology. Now, I will say that we are also developing a reference implementation so that you can see what the methodology looks like in real life. I don't claim that those tools will be perfect. I don't claim that those tools would be the tools you'd want to use forever, right? I do, however, think it's important to show the methodology in living, breathing form. And so we will make selections. And we'll come back and talk about that more in a little bit. But we will make selections in these various things so that the reference implementation has an implementation. All right? Now, in support of using the readily available open source software tools, we're going to need to provide an integrated data model for capturing that complete source we talked about, the BOM data, the assembly data, and anything else that we need, right? And it needs to be in a way that is compatible with open source software development tools. In other words, these data models, when we store them in the computer, they need to look like source code. Line-oriented ASCII files organized into directories on disk, right? Why line-oriented? Well, it's so that individual properties can be diffed, right? If each line represents an individual property about a part or about a step in an assembly instruction, when I make changes, I can use existing version control and diffing tools to figure out who changed what and how, but only if I'm line-oriented in ASCII. Organized into directories, right? Because that's how these source control tools see projects, is source files in directories. And those directories have meaning, so they need to have meaning in the methodology, right? So, and then finally, just a reminder that this integrated data model has to capture that BOM data, the assembly instruction data, and any of that other supporting material, right? And we need to ensure that it's extensible, because we already talked about how supporting materials is a catch-all, so we remember to have an extension point. So this data model is one of the primary places that has to be extensible. So that begs the question, what is next for our work in open source hardware? Well, there are three things. We need to fully define the DOF methodology. We are actively using this work to support additional aerospace efforts that OSHW has invited us to participate in. And we need to provide that reference tooling for all of these efforts so people can see the methodology live and breathe, right? Okay, so let's talk about fully defining DOF for a few minutes, okay? Earlier work, the work that you saw referenced in that view that talked about what is DOF, right? The GitHub Mach 30 DOF, DOF.adoc, right? We were defining DOF using custom YAML data structures for data storage. And the YAML files are absolutely line-oriented and convert to JSON easily, so we really like that, right? So we can put these data models as easily into a REST API as we can in a Git repo, right? But this was deeply in-house. We were writing a lot of tooling that wasn't about DOF, it was about managing these YAML files, right? Well, we've discovered that there is a project called LinkML that lets you define YAML schemas. And it has a bunch of tooling built in to support creating them, verifying them, and validating them, and working with them. So we are in the process of migrating from our custom YAML data structures to LinkML. And I have to say, while we like with every open source project, we've bumped into a couple of bugs that we're supporting that team's efforts to fix, and we're providing feedback and all that. That tooling is so much better than trying to build this from scratch. We cut off years of development effort that wasn't necessary and wasn't part of the project. Our reference implementation for DOF leverages npm/yarn for package management, meaning users will be able to npm install Arduino Uno or yarn add Arduino Uno to add an Arduino to their project for open source hardware. We've demonstrated this with earlier revisions of this, and as the LinkML port happens, we'll re-demonstrate this with that version. We chose this partly because we want to make sure that the methodology can be supported by both web apps as well as local apps, and JavaScript is just still one of the predominant frameworks for that. And it's one of the few package standards that has at least two, I think we're now up to 3 independent implementations of. So even if npm goes away, I don't think yarn is going away anytime soon, right? And so we figured this had a little bit of future-proofness to it, and the standard has demonstrated that it can be created multiple times. So even if someone had to create a tool that was npm yarn compatible, it's been done several times, it could be done again. So it buys us some future proofing. And then all of this we're using in the reference implementation Git, and we tend to store our stuff on GitHub. GitLab would work just as well. Git, I'm sure, would work just as well. Pick your favorite way of hosting Git projects. But once you have all the data modeled and you have the right build pipeline, you can then render out assembly instructions that include all the details about the parts that are consumed in this, the tools that are necessary in this, any precautions or hazards associated with these materials or tools, as well as the detailed step-by-step process to execute this part of the assembly process. And again, all that is coming from tooling. Speaking of tooling, right, well, I'm going to do this first, and then we'll come back to tooling. One of the other big things we're doing besides completing DOF itself, right, is using lessons learned in DOF and some of the tooling in DOF to support activities at OSHW, especially around aerospace. So our team that's working on DOF is actually splitting DOF into a base schema, a base language called M30ML or Mach 30 modeling language that has the more generic capabilities in it. So instead of focusing on the parts and assembly instructions for a project, this is where we have the core concept of the definition of terms, of actors, of activities, of structural modeling, right? And then we can repurpose this, for example, to define dry source code for aerospace development standards. Because if you're going to do aerospace systems in the real world, you have to get them certified. Just ask the FAA. They're going to tell you all about the things they're going to want to see, as well as other standards bodies, right? And a lot of what they're going to say is, we want to know what standards, what internal processes are you adhering to for configuration management, for project management? How do you decide to let a change into your project? What's your change control process, right? Well, we do a pull request. Yeah, that ain't going to cut it with our friends, the FAA, right? But unfortunately, most of the standards that are out there are proprietary, and they're locked up in the big aerospace companies, right? So we need to be able to write our own, but guess what? They're all cross-referenced too. It's the same dry problem, right? You go to make a change in the document, and suddenly you're counting how many different places does this thing show up, and you better hope you got them all. Well, the same stuff that lets us do projects dry for open source hardware lets us do standards dry. So we are taking the precursor, this base schema, and making it available to develop standards with. And then back to the reference tooling, right? So I talked about like npm and yarn, right? And Git. So our focus is on a combination of existing tools and the things we minimally have to develop. So in terms of the existing tools, we're going to use Git. Again, the methodology is not going to force that, but we're going to certainly use it. We like GitHub, right? You like GitLab? Fine. You like SVN? SourceForge, I think, is still a thing. I think. I don't know. I haven't been there lately. Again, npm yarn, for all the reasons we just talked about, plus I just get a kick out of going, I want to say npm install Arduino Uno, and all the data comes into my project nice and clean and neat. And then there's a whole bunch of there's a rendering layer that's really important that we don't want to have to develop the internal tooling around. We want to leverage stuff that people already do all the time, right? Because you need to render out a PDF of the assembly instructions, of the operating instructions. You need to render out a purchase list, right? I need to go order 2 Arduino Unos, right? This much wire, these many resistors, and a partridge in a pear tree, right? For the whole project, not just one piece of it. So I'm going to need the ability to crawl over the model, but then also render what I pulled out of the model. So we're using Pandoc, Jinja 2, Markdown. This stuff should sound familiar if you've done any web development. These are very common tools to do that, because rendering views on the web page is not dissimilar from rendering views of the assembly instructions, for example. Now, what does that leave us needing to do in terms of new tooling development? Well, we got to really focus on that data model and the creation of the data that adheres to that data model, the maintenance of that, right, and the query and content extraction. Okay, in other words, we need to focus on all the CRUD operations for this data model. There's a bunch of files and directories on disk so that Git can even understand what our project is. So, in summary, we just discussed what's next for the project for DOF, right? And the related efforts for open source hardware projects and aerospace activities. This work directly addresses the lessons learned from the need for open source hardware development methodology from that retrospective of the Shepard Test Stand project, which again makes Shepard a really, really great case study in open source hardware for aerospace and open source hardware generally speaking. What do you guys think?
Question time?
Yeah.
All right. Questions?
Yeah.
Yeah, so with DOF then, so are you essentially taking like the data sheets, and that would be in like in PDF format for like a microcontroller or whatever, and putting it into the YAML format then? Is that?
So what I would say is we're going to put the minimum necessary, right? And then we would attach the vendor's data sheets as a supporting material for something that's purchased. However, if I was, say, the Arduino organization and I adopted the DOF methodology, I would put all the data that goes into the data sheets in the project, and then one of the things I would query and render out, Pandoc and would be the data sheet. Make sense? Yeah. For stuff that we don't own, we want to model as little as possible so that we can do our project. And for our projects, we want to model all the details necessary to provide that information to third parties.
Hi, this is amazing. I have worked at aerospace at one time, and then I've worked in medical, and I'm tempted to ask, when you turn over a project, like in medical is a lot like aerospace, to get validated, you need to have requirements, and then you have to have traceability and test engineer, test procedures, test requirements, all those things. Is there anything that you have relative to requirements and testing?
Yeah, that's a great question. And 100% that medical and aerospace have a lot in common about that. In fact, some of the folks at OSHW we were working with were as interested in developing standards for medical, open source medical devices as they were for open source aerospace projects, right? One, See the third line of all the supporting materials. The point is absolutely to build in space for extension points. Right now, our core modeling, the way that we approach this project is predominantly through user stories. So we are modeling user stories to build and supporting traceability from user stories to implementation. But there would be no reason that we couldn't also model requirements in the same, in M30ML, and let those flow into DOF as well.
Your user stories are required.
They are, absolutely. They're just a particular shape, yes.
Supporting documents?
They would be supporting materials. Yes.
I wonder where it fit into.
Yeah, it would be supporting materials. And if enough projects started saying, you know what, we really, really want to go through some sort of requirements process. I don't know that that's going to be the case for a lot of open source hardware, but if you got to a point where the movement was like, oh yeah, this totally needs to be a thing, right? We would promote some sort of requirements management into a third bullet and still have a fourth bullet that was everything else. Because we're responsive in that way. We want to be responsive and learn things as we go along.
Now it's user story, but how do you make a user story for a fuel pump?
Okay, so we're two things. So the follow-on question for those out in video land and in YouTube permanently is, okay, user stories are a form of requirements, that's great, but how do you make a user story for a fuel pump, right? Or other pieces of hardware, right? And the short answer is I don't think you do necessarily. We are doing the eat your own dog food thing, right? So as we develop DOF, we're developing it in M30ML, right? So M30ML has a concept of user stories because that's what we need in it right now. We get to a project where someone's like, oh yeah, we need real requirements, the kinds of things that in commercial space would wind up indoors, right? We do one of two things. There are actually a couple of open source, including one that is all ASCII focused. I forget its name, but if you find me afterwards, we can exchange contact information. I'll go look it up and send it to you. That is a direct competitor of Doors that's all text files in a Git repo. So one thing you might do is say, let's integrate DOF with that, because then we don't have to reinvent requirements management. The other alternative would be, if that didn't work, right, to implement requirements as another one of those pillars, right? But until we have to, right, MVP, minimum viable product, get her done, use what we're actually building, right? Right now we're just tracking user stories for DOF. What are the user stories of DOF itself, right? I want to be able to fork up open source hardware project as a user, But yes, you're absolutely right, and this is why that extension point is in there, because we know that this is not for everybody a complete picture. It's very MVP. Great question.
We have more time.
I want to ask, since you guys are basing this on the JavaScript ecosystem, are there any plans for type safety between components?
That is a really interesting question. One of the ways in hardware that I would argue, and Sean, my co-conspirator over there in the back, midway back, is going to go, oh, you're saying my words now. In hardware, one of the ways that we enforce compatibility, because type safety is in part a compatibility thing, right, is through the definition of interfaces and the enforcement of interfaces, physical, mechanical, electrical, and software, and I think one more I'm missing. Wow, I've been too long out of school. Anyway, so we have had a number of conversations about creating support for defining interfaces and laying an interface onto a component, saying this component is expecting this interface from what it's plugging into, and then saying this other component has that interface. And then if you try to say, I'm going to connect this part to this part, and they don't have compatible interfaces, that you would get an error. That is absolutely a more advanced thing than what we're doing right now, but it is a constant conversation because, again, once we start talking about certification, especially in aerospace or in medical, these are very important tools for being able to demonstrate safety, compatibility, and function. Great question.
To follow up, I mean, one thing that's always the case, is that things are really sort of, you peel back the layers of the onion, it's
Yeah.
systems of systems of systems of
Yes.
systems. And for instance, in software, you have this notion of a hierarchical DFA.
Yep.
If you had a safety kind of methodology or
Yes.
notation, you would have to sort of be able to, I'm sure, have snap-in components that are inside of other components.
Yeah, well, and that whole, it's systems all the way down, it's turtles all the way down, is one of the actually baked-in principles of this, that a project is itself just a component that could be embedded inside of some other project, right? And so you would be able to, at each of those project points, right, create those interface boundaries, create those safety and security boundaries. Because, wow, now how long before I start talking about, so I put my, Shepard 17.3 test stand on the internet so I can share it with the students over in Georgia, right? And then someone's like, okay, did you consider cybersecurity for that thing so someone doesn't turn the motor on while your face is in front of it? Oh, yeah, that. So MVP, and then clearly a lot of layers to build on top of it, but it is absolutely built around this notion of its components all the way down. Great questions. Thank you, guys. Sean, you're looking like you're going to say something. Like you just can't contain yourself.
I'm laughing because one of the ontological modeling languages that we were working with maps to a framework called Turtle. So it, in some instances,
It really
literally
is turtles all the way down. Thank you.
One more up front here, or as many more as people want.
Yeah, we got time. We got another 15 minutes easy. As Captain America says, I could do this all day.
I was also curious as to how much of the stack you guys want to cover. Do you guys want to cover hardware description, or is it just physical stuff?
Okay. Right now, what we want to do is cover just enough that we can take projects like Shepard, and I've got a couple other projects of my own that are personal, right, that are not related to the aerospace work I do. And some of the projects that Sean's been a part of that have also gotten certified as open source hardware, and recertify them using DOF-based projects to just get the process going. We are still very much in a modality in the open source hardware movement, and I say this as a member of and who fights this battle daily as well, right? Of not having a clear-cut way of especially that forking, branching, remixing kind of stuff. There's a lot of projects that just do code dumps, right? That Michael was talking about in the last talk about, we did all our work behind closed doors and we just put the answer into GitHub. That was it, right? And that's not gonna facilitate the full definition of open source hardware. So what we're really right now focused on is that minimum level to take projects that have already been certified that involve files in 7 different repos that have no true connectivity to one another, and the moment you want to, that you could never maintain. We stopped development on Shepard because of the maintenance nightmare. We just stopped. We were like, we cannot make this go. It is too heavy, and it's not a big project, honestly, right? It's a few dozen components, maybe 60, maybe, right? And we couldn't maintain it anymore, okay? So we just want to, right now, the focus is get projects like that done in the DOF methodology so we can demonstrate real remixing, real, take this project and make it a piece of another project, and then see what the open source hardware, how the open source hardware community responds to having a process that actually answers the mail for the definition. And if that is requirements, right, we're going to go into requirements land. If it's more of the certification stuff, we're going to go in the certification direction. If it's more into interfaces, we're going to go into interfaces. But it really is, let's just get something that we can all start using and rally around, where one repo or series of truly chained repos through dependency management can actually define a project in a way that's supportable. Great question. And I'm going to duck. Sean's talking again.
No, just a quick comment that, so my group, the I work with a nonprofit that's developing open medical hardware, and this emerged out of during the pandemic when we needed a means to facilitate how do we source materials in a constrained supply chain, so to speak. And one of the considerations that the DOF data model, at least the MVP version, considered was alternative components.
Yes.
Right? And we started, actually, for this upcoming Maker Faire, we are revamping one of our current bill of materials data to actually have alternative components, because we realized if we want makers to be able to produce these in their own garage, we need to switch from a surface mount to a through-hole option for our PCB assemblies. And so we actually, in our BOM data, have an alternative option to consider. If you don't have the equipment to build the surface mount component, you can use the through-hole option. And so taking this approach of modeling your BOM as opposed to just documenting in raw PDF or what have you, like it's just is becoming a useful use case like in our project.
And that's what we want to do, is support use cases like that so that we can build that community and then figure out what the community needs most next. We figured this much out on our own because we ran into all these walls. We had all these successes and still ran into all these walls.
So I guess this is maybe a little bit of a different thing, but when I first came to your talk, there's a large amount of work in the sort of the processor arena around open source, like Spark 5, it's a huge example. And if you're looking at FPGA programming, there's a whole kind of parallel open source ecosystem for doing FPGA stuff.
Yeah.
Is the stuff you're doing at all rubbing shoulders or sharing lessons learned from those kind of folks?
Not yet, because in my, and this might be just my lack of experience in EE, because I'm a systems engineer and a propulsion guy, right? That's where my education is. But my understanding is so much of that is still very software looking, whereas I need to print something on my 3D printer, and then I need to stick an Arduino inside of it and use these thumb screws to hold it down and print another thing and stick it on top with the LED poking through the right way. That doesn't look anything like that, right? It's a very human-intensive process. Like I said on that, like, the human is the compiler for the overwhelming majority of these projects still, right? And so I don't think that we overlap as much, other than to say, yeah, like they've figured out ways to emulate the software approaches, we need to figure out ways of emulating the software approaches, but when a 3D printer is involved, or a laser cutter is involved, or an Arduino is involved. Fair, though, and again, not my area.
I have a question. I think this young gentleman back here and I would like to know, if we go to the Shepard site and print out something, it'll give us instructions and we could build a rocket? Is that
Not a rocket, a test stand.
a test stand
So
for a
let's go back,
rocket.
like, I cannot get enough of these videos, so I'm going to do it again. I'm totally breaking the rules. I'm sorry out in YouTube land. I'm going to get, like, the hook on me. Let's go back and watch. Come on, where are you? This one. Okay. Now, so here's what's going on. Right in here, do you see this thing right there, bud? What's your name, by the way? Oliver. I'm Jay. Nice to meet you, bud. All right, Oliver. See this thing right there? That is something you can buy from Hobby Lobby that is called a rocket motor. It's a one-time use thing to make a model rocket fly, okay? Now, what this does is lets us operate that motor on the ground so we can measure how well it works. Because in engineering, one of the most important things we do before we fly a rocket is we test the living daylights out of it, because we don't want it to break while it's in flight. Rockets are expensive. The satellites we put on top of rockets are very expensive. People are out a lot of money, and people can get hurt. Even worse, people can get hurt when rockets don't work right. So we test them a lot. And the way we test rocket engines and motors is with what's called a test stand. This thing right here that's holding that motor is our test stand. That's the thing that you can go out to Open Design Engine and download the bill of materials, the list of all the things to buy, the assembly instructions, how to put it together, right? And the operating instructions, how to safely test a rocket motor so you don't get hurt, and that you can collect that data, which looks like this. And that data shows us the performance, what's called the performance of the motor. The motor produces thrust. Thrust is the pushing force of a rocket. It's what makes the model rocket fly off into the sky, right? We measure thrust in pounds or in newtons, the same way we measure the force of gravity, weight, okay? And so that curve is the result of collecting every 100th of a second, I think it was on this test stand, right? How hard the rocket was pushing against the test stand, right? And then we can graph it, and we can say, did that rocket motor perform the way it was supposed to? Did it work the way Estes said it would, okay? Now, Estes is a professional company and produces hundreds or thousands or tens of thousands of motors a year. I'm not really worried about whether or not their motors work. In fact, I'm grateful that they're going to work almost all the time, because then I can teach someone like you how to collect data on a test stand and how to interpret data on a test stand, because we know what the answer is. The answer is what Estes publishes. They show us this motor will do this in this many seconds, and this looks like that. And as long as our data looks like what it should look like, we can go, we had a good test. And then if you're the Jones boys, you can take that same concept and use the same basic hardware to test a motor that you built on your
Firing
own.
in 5,
And that's what they did and won a bunch of science fair projects with.
1.
All right? This test stand, not open source, just they use parts of our open source stand. That other test stand, though, totally open source, and you could build it like the museum, the Coca-Cola Space Science Center did, absolutely. And if you want to get with me afterwards, we can exchange contact information, and I'll make sure that you get support if you run into questions. Because we've mostly shut down ODE, so you can't use the forums anymore, but you can email me. Great question. And like I said, I love this stuff, and I cannot get enough of them.
Great. Nobody else? I think that's it. Thank you so much, Jay. Big round of applause. That was awesome.
Thank you, guys.